Good morning, everybody, and thank you for this invitations. Fani has given some nice introduction to NV centers. So I'll be looking at a different aspect of NV centers, basically on the photonic properties and more. So the title is Tailoring Diamond Color Center Emission Using Photonic Structures. So I'll input these NV centers in certain type of structures and try to modify its emission spectra. So I'm from Department of Physics at IIT Ropar in Punjab. And as I just mentioned that India is a lot of diamonds polished. This is some of the diamond grown in Surat by a company called Super Hard, where we are collaborating to make a quantum grade diamonds in India. So they supply these diamonds to us in our lab. We test it, we give the result back to polish them, to modify them more for the kind of applications we are looking. And if you take this piece of diamond and shine it with a green light like this, you see a red color, it's a fluorescence. And we are trying to modify this fluorescence, some of the, to make this diamond color centers is a good system for many applications in quantums. So I myself from a photonics background, we are trying to learn into these diamond-based quantum technologies. And so I'll share you some of my learning, some of our understanding. So just before moving to the technical details, I just want to introduce our group. We started in 2014 at IIT Ropar. We primarily work in light matter interactions in different engineered photonic structures. We work in photonic crystals, disordered photonic systems, and in meta surfaces. So these are some of our recent work. And of late, we started interested into NV centers in Taiwan. So this is a confocal map in our lab where some of the NVs are shining. And very recently, probably last 2 years, we also ventured into color centers in 2D materials. And this is another nice system to work on many optical and spin properties. And I'll show you this result of 2D some other time. We just got some interesting results very recently. Okay, so there are a lot of holes about quantum emitters in solid systems, especially in the last 10 years or so. Especially such of these quantum emitters can give single photons at room temperatures. And it can have single spins manipulations, which are even millisecond coherence time. So it's a very good candidate for many quantum technological applications. And it can have many optical responses at many wavelengths from blue to near infrared. And some of the system can be easily get into photonic structures to make it their things which are much more efficient. So these are some of the work done around the world, where the early works on quantum dots in some micropillar cavity. And this is a silicon carbide. You can see that there is a periodic nanowire structures, and there is a diamond nanowire single photon source. Basically, they try to create periodic NV centers in these nanowires. And there are quantum emitters in 2D materials. And all these emitters, you can see that it is somehow put it inside a electromagnetic environment or a photonic structures. And I'll tell you in my talk why we need this and why we have to do this. So the diamond is a wide bandgap material. It's quite transparent, but due to these nice defects and type of defects, it shows nice sparkling colors. It becomes very interesting for jewelry. And as I said, India in Surat is quite a lot of work on polishing diamonds. And there are a lot of growth of artificial diamonds now because of the Ukraine war, because the diamond supply from Russia is stopped. So we have a lot of opportunity to grow this diamond artificially in the lab. And this diamond has a lot of defect centers spanning from 450 nanometer to 800 nanometer. And depending on the type of vacancy or defects you have the optical properties difference. And diamond is not the only material which can have these properties. There are material like silicon carbide, even hexagonal boron nitride. It's another system which is also shows similar properties at room temperature, sometime with a better optical response. So what is this NV center? Okay, so we take a diamond lattice which is made of carbon atoms, and you have a nitrogen atom here which is externally placed, and near to that you have a vacancy, and this pair is known as nitrogen vacancy center. Okay. So one can have, depending upon the electronic configurations, you have two charge states, NV0 and NV minus, and depending on then you have a different spin states. And one can optically excite these NV centers within the diamond lattice, and you can also manipulate the spin properties using microwave and magnetic fields. So the established energy level diagram of NV center, we have a triplet ground state, and then you have a triplet exciter states. And if you excite this with a green light like this in the lab, and you take the population from the ground state to the excited states. And on the way back, it can take two ways. One is called a spin conserved transitions, and it can have a spin selective transitions. And you can, this zero field splitting, as explained very detailed in the previous talk, that this zero field splitting is around 2.87 gigahertz. So you can apply microwaves and manipulate this spin state in the systems. And by applying a magnetic field, you can even do more things like magnetometry and quantum sensing by using an effect called Siemens splitting. So this is the, and if you look at the NV emission spectra, so the textbook example, you have the electronic ground states and the excited states, you have a lot of vibronic levels. And you excite that, the population goes from 0 to 0, what we call is a zero phonon line transition. It is a pure electronic states. And you can also a lot of vibronic contributions. So your NV center emission spectrum consists of a zero phonon line at 637 nanometer, and you have too many contributions from vibronic level. And if you measure these emission spectra in the laboratory, this is some measurement from our lab, intensity as a function of wavelength, you can see a very broad emission spectra. And the zero phonon line at 637, which is a pure electronic transitions, which is very feeble and weak. And this is something which is quite interesting for many applications in quantum technologies, where because there's no coherence, it's very coherent states, and all these phonon sideband induce decoherence in the system. So people try to avoid it somehow. And one parameter which we used to define in the NV literature is what's called Debye factor, which is the amount of emission which is getting into the zero phonon line compared to the total emissions. And this NV center has only 2 to 3% Debye factor at room temperatures. And if you cool down the system at low temperature, you can suppress all these phononic contributions, but still the emission is 4 to 5% only. And the emission rate is also very, very slow in the system. So ideally, one look for a system, a quantum emitter, which has a wavelength intensity as a function of wavelength, which is 10 around the zero phonon line, which is not existing. So we have to make it somehow close to that. Okay, so the obvious question is to couple to photonic structures, which I'll show you how we did it, and or explore other quantum emitters in diamonds or in other systems like 2D materials. A lot of research recent in years happening. Okay, so when we talk about diamond samples, usually we get two types of samples. This for students, and we classify in two categories. One is called bulk diamond samples, which is either CVD ground or HPHT, high pressure, high temperature ground sample. You get these pieces of glass like in your hand. You do a typical confocal map, and you identify an emitter, and you do all the spectroscopy or spin measurements there. And this is a real picture of the samples, some of the samples in our lab. One can also buy these nano diamond samples, which is like a colloidal particles with the sizes from 5 to 100 nanometer, which can also have NV centers, because NV center is a very system, it does not have photo blinking or photo bleaching. So we can integrate for many biological applications where these nano diamonds are quite interesting. And since sizes are very small, this can put it very easily integrated to photonic structures, unlike making a photonic structure in diamond itself. So as many applications in the last talk also mentioned, that there's an excellent fluorescent biomarker because no photo bleaching, it's a very stable system. It can have temperature, magnetic field sensing, electric field sensing. And one of the applications is a magnetometry, which is now a system which is commercialized by a company in Switzerland, where you can buy and use it NV-based magnetometer in the lab. And of course, in the quantum photonics technology, you have this system can give a single photon emissions, where one can measure Hanbury-Brown TIS experiments, you get a G2 value of 0.38 at 0 time delay. So these are some of the properties, but have said all the nice thing about NV centers, there are a lot of disadvantages this system has, especially in terms of photonics perspective. One, as I already said, is a very broad emissions with huge contribution from the phononic sidebands. So we need to suppress that somehow so that you get only pure electronic transition into the business. And when you pump it with the systems, there can be ionization process, though this charge state conversion happens. So NV minus can go to NV0, and you don't want to happen that. And the other thing is, especially in when you want to make a very bright single photon source, the lifetime is very, very large. The bulk diamond shows 10 to 15 nanoseconds, whereas a nano diamond in the literature, the argument is from 20 to 40 nanoseconds. So you have a very slow emitter, so you want to make it faster using photonic structures so that you can create on-demand bright single photon source. So what are the solutions for that? And that is where the photonic structure, especially the engineered structure, come into picture. So as you know that the basic physics, you have a two-level system. The spontaneous emission depends on the dipolar moment and also the density of photon states. So if you have a system where you can control the density of photon state at certain frequency omega, you can control the decay rates. So earlier, the champions, the Purcell effect and the Kleppner and then Yablonovich paper, they talk about creating structured environment structured electromagnetic environment like photonic crystals or cavities, where you can couple these quantum emitters and try to play with their emission properties. So this is some 2D photonic crystal picture where you have array of holes, you have a quantum emitter, and you can modulate this emission by using the band gap properties, or you can trap these emitters in typical cavity structures, and with the resonant mode sets the wavelength you wish, you design the cavity like that, and you can do a lot of nice things about them. So we were working on developing these kind of structures and understand light matter interactions from long time at IIT Roper. So we thought, why not use this kind of structure coupled with the NV sender and see whether we can control the NV sender emission properties. So if you look at literature, there is a whole lot of work happening around the globe in the area of coupling NVs especially, or other quantum emitters with photonic structures. There are some groups working on pillar kind of cavity structures. You have a layered structure, then you have a cavity here, or you have a one-dimensional photonic cavity structures or nano beam cavities. And people are also using these silver cubes trapped with an NV center and a nano diamond here, try to modulate the emissions. And there is some groups working on hyperbolic metamaterial. Basically, these are metal dielectric stacks coupled with NV centers, or using the mere resonance of the micron-sized diamond particles. And this is something more, very active area where you create photonic crystal cavities, where you have periodic arrangement of dielectric constants. And you can see there is a cavity here, and you have a NV center trapped there. And you do an emission measurement, a decay rate measurements. In the reference sample, you have around 13.7 nanoseconds. But when you do an experiment in the cavity, you get around 4 nanosecond length. So you could, by trapping the NV center in this cavity kind of structure, you can speed up the emission process. And this other work is what we people made is nano beam cavities, like a material where you have an array of holes and you try to create NV center. But you can see here, they try to match the cavity mode very close to the 637 nanometer, which is a zero phonon line of the NV center. This is a very recent work. Last week it appeared in Physical Review Applied, where they made a hyperbolic metamaterial, and then you trap these NV centers. It's a cartoon picture where try to see the increase in the sensitivity of magnetometry and other experiments. And this is one work from TIFR, Mumbai, where instead of NV center, they made these kind of structures, and they have a quantum dots and try to manipulate the emission properties. So those are mostly with the dielectric. But one can also look at the plasmonic cavities, which has a bit better control, but you have inherent loss with the plasmonic system. You can control the emission properties. One of the things which you often see in literature that the people talk about cavity coupling with the enhanced emission intensity. You can see that by coupling a dimolecule in a cavity, around 60,000 increase in emission intensity. But if you look at the decay rate, there is no much change. So this is something which is very important when you couple any emitter with cavities or a photonic structure. What you need to have a changes in the decay rate. Otherwise, you just have a filtering effect, nothing more going to happen. So we'll show you some of our work now. So we were making these photonic crystal, like these kind of colloidal crystal samples. Basically, these are submicron spheres. We assemble them in a very controlled way, and you make a photonic crystals. And when you shine a light on these structures, a certain band of wavelength is reflected back. So we call it a band gap. So we brought this work we started around 2016-17. So we brought at that time around nano diamond, which was an ensemble of NV centers from a sigma Aldrich. And we drop casted on top of a photonic crystals. And we wanted to see, do this photonic crystal, this colloidal based low index system can change the emission properties of NV center. So you can see that we made a photonic crystal, one which has a band gap around 450 nanometer, which is a reference sample because the NV center emission is from 600 to 750 nanometer, and this does not have any effect there. And this sample, where we call it a red color sample, which is our main sample, where it matches, the band gap is in match with the NV center emission properties. And what is more important for photonic band gaps or photonic crystals, the band edge effects. So we can see that at this photonic crystal, the band gap, the band edge is close to the zero phonon line. So we expected a cavity-like effect at these band edges, even though there is no spatial cavity in the system. So we developed a very simple experiment long back to collect the emission spectra. So our reference photonic crystal with the NV center, you can see that the emission spectra does not show any change induced by the system as expected, because this is a reference sample. And when we did this experiment, the first experiments where we excite this NV sender from the back of the photonic crystals, we collect the emitted light, and you plot the intensity ratio, you could see that there is a decrease in the emission intensity at the wavelength from 660 to around 700 nanometer. And these are photonic contributions which is suppressed due to the band gap effect. And if you slightly increase the pumper, you can see that the zero phonon line is bit enhanced, but it is really a statistical thing. It may not work always. And as I said in the previous slide also, the lifetime does not show much changes. Okay, even though intensity show huge changes, but the lifetime does not show much changes. So probably because of these systems are quite a lot of disorder and also very low index contrast. But even though it shows a system where you can really engineer the light, the emission from NV sender using these simpler photonic crystal structures. So we did a bit more experiment. We reversed the measurement geometry. Now we are collecting from the top. The photonic crystal now act like a mirror. You can increase the emission intensities. Like in many biological applications where you want more NV intensity emissions, you can use this geometry. And we submitted this to optic letters, and it got accepted very fast, and it was editor selection. And there was an article in Physics Today about our work, how to make diamonds shine brighter. Okay. So then later we did a lot of experiments. We published one in Physics Review, then in Journal of Optics. And recently we did some theoretical work to show that, to support our experiments, that indeed the photonic crystal system can enhance the emission intensity. Okay, but again, you see there is not much change in the lifetime emissions. So this structure, if you remember my picture, these are multi-layer structure. There are around 30-40 layers assembled on a substrates. So then we thought, instead of doing this kind of system, can we have a real cavity kind of systems? So that comes to what we call as flat structures. So we're from Punjab, and Punjab is really a flat land. Okay, so we call it a flat photonic structures, or in literature it comes as metasurfaces. So you take these kind of dielectric spheres of submicron diameter, or scatters, or different shapes, and you arrange in certain symmetry. You excite with it. You can create. They excite these electric dipole, magnetic dipole, other higher order poles. Then you can interfere them in such a way that there can be a system where you get a complete forward scattering with a near zero backward scattering. This is in the literature what is called Kerr conditions. And at these conditions, you can localize light inside the material, even though there is no spatial cavity. And once you have electric field is localized, your dipole moment dot with electric field, you can enhance the local density of photon states. So this is the whole idea of what people nowadays talking about quantum metasurfaces. You have these kind of systems where you create quantum emitters in these individual scattering, and you play with these multipolar contributions. So we thought, since we're able to make multi-layer structure, it would be easy to make a single layer structure. And it turns out it was even much more difficult to make these structures, these one layer of polystyrene spheres. So you have a substrate, and this is one of 700 nanometer microsphere on the samples, on the substrates. And when you shine light, you see two dips, which corresponds to one is grating mode, because there is a subwavelength grating, and this mode, which comes close to around 700 nanometer, 733 nanometer, which can localize some field between these spheres and the substrates. And that means this is a low index metasurface, which can control, which can enhance the, or which can affect the NV sender emission properties. So the student put NV senders on top, and we try to do the measurements. And we see that if the off resonance decay is bit slow, but when you have on resonance, that is with the Venda surface resonance match, you get a very fast decay in the system. So by using the simpler structures, we can engineer the light emissions from the NV sender. You can see that when we did a lot of measurements, that these distributions are quite distinct. And these are very simple structure in the microsphere, because we don't have a lithography lab to make these high index systems. So, but once you have a clean room facilities, you can make these kind of nice silicon or diamond cylinders, and you implant with a single NV senders or single emitter. You can even get, theoretically, we calculated around 400 times enhancements, and you can suppress all the phononic contributions. And this result, analytical and theoretical calculation, we published recently in Advanced Optical Material, and this was a cover page also. And in the literature in this year and the previous years, there are excellent review articles coming, how to use these kind of structures to enhance on-demand single photon emissions or metasurface for quantum photonics. Because it's a very nice system which gives very high Q factors, which can easily control the quantum emission. So all this previous in our work we show is a colloidal based system, which is very tough to make it and it has a lot of disorder. So can we make much more deterministic structure where we can precisely place an NV sender at some position today and tomorrow and after, so that I have a control on fabrication as well as experiments. And there are, we look at something which is feasible for us at IIT Roper. So we come up with this idea where we have a metal dielectric structures. So basically it's a DBR, a distributed Bragg reflector, low and high index layers. Then you have a silver layer on top of that. In the literature, this is known as TAM structures. So if you don't have a silver layer, you calculate the reflectivity using a simple transfer matrix method. You have a photonic band gap or the 1D photonic band gap. The moment you place a silver layer on top, you get a cavity mode at 640 nanometer. How do you make sure this is a cavity mode? We do a field calculations, and as the field as an intensity as a function of the spatial distance, you can see that at the surface, this field is getting localized. Around 18 times localization is there. And and we engineered at 640 nanometer, and if you send a 550 nanometer light, the light gets reflected back. This is known in condensed matter system long back in 1932 by Igor Tam at the bound state of electrons on crystal surfaces. So you have a crystal but for electromagnetic radiations, you can also create these kind of bound states for electromagnetic radiations. And that's where this, in the literature, this is known as TAM structure or optical TAM states. So this is tunable by changing the spacer thickness or angle. You can get wherever you want it. And one of the most exciting aspects of TAM structure in comparison to conventional surface plasmons, you can excite both transverse electric as well as transverse magnetic polarizations. And you can even get at 0 degree. But in the conventional surface plasmon, you have to have a very complicated experiments, and it's only possible for TM polarized light. But this is much more easy and to do experiment with these samples. So what our idea was to create, you have a conventional TAM structure, and you create a few more layers on top of that. And we call this an asymmetric TAM structure. And why? Because in the lower part, you have a larger number of layers, and in the top part, you have a few layers. So it's not a symmetric mirror system, but rather an asymmetric systems. So we simulated this. This was done mostly in the COVID time. So we tried to get a TAMS mode at 640 nanometer. But we also got another states, which is another TAM states. And why so we get? Because there are two interfaces. There are dielectric interface from metal and here, and there is a dielectric interface from the top mirror also. So we expected, yes, we do have two states. But we were actually focusing on this one. And if you look at the field calculation now, you can see the field is now 50 times. In the previous case, it was 18 times. So we are able to localize more light at this cavity layer using this special symmetry or special model. So we thought this could be a better system to give a more control on the light emissions. And we did the Purcell calculations, means the amount of light we can enhance, and you can see that at 640 nanometer, we got an enhancement, and also the light collection efficiency also is very much enhanced at 640 nanometer. Okay, so the more details can be just recently available in advanced quantum technology, and we'll show you in the last of my talk our attempt to fabricate this system in the laboratory. Okay, so some of our very recent research. Okay. So COVID was over, so we back to the lab, and the last 2 years we are developing setups or experiments where we can image single NV centers or even few NV centers. So what we developed at IIT Roper is a state scanning confocal microscopy. It can do imaging, spectroscopy, and correlation like Hanbury-Brown-Tisse experiments. So you have because of a laser, you excite with a high energy objective. The sample is here. The picture is given here. The sample is scanned in an XYZ stage. And you can collect this emission and it's sent back to a spectrometer for a spectral measurements, or it can send it to a single photon detector for lifetime measurements. And we can also do a intensity correlation measurements. And so as shown here, so this is a typical confocal map we get in our lab. You can see that a lot of nice NVs are placed on the substrates at different locations. And so this is the actual picture of the lab. So you have a camera to image the sample. Then you can have a PL measurements by using a flip mirror, and you have a HBT, Hanbury-Brown-Tisse experiment to do a single photon measurement, single photon test experiment, which we have successfully done it. And so let's move to the experiment now with a few more single NV centers. So we wanted to have a cavity, photonic cavity structures at 640 nanometer. So first we start with a very simpler cavity. We call it a metal cavity. So you have a substrate, you have a 80 nanometer silver layer, then you have a 100 nanometer tantalum oxide layer with a lot of NVs are dispersed. And you have a 30 nanometer top layer because you have to have a very less thickness because you have to get the light out of the system. So we simulated this and we got a cavity mode at around 640 nanometer. And when we measure in our lab with the reflectivity spectra, the cavity mode is also at 640 nanometer. So this is what we designed. It looked very simple, but it took quite some time for us to get the kind of sample we wanted. Even though this cavity looked very simple, but in the literature, this has been used for experiments like strong coupling regime, cavity catalysis, and published in this PRL and HCOM. And if you look at the field calculations by FTTD simulations, you can see that within the cavity layer, the field is quite enhanced or localized. So that means if I place a dipole here or an NV center here, I should be able to control the emission properties. And that's what precisely we did the experiments. So we fabricated this sample with a NV center dispersed on the cavity layer. And we mounted this sample on our experiments, and we took a typical confocal map of 100 by 100 micron. And we can see that there are a lot of nice bright spots. All may not be NVs, some may be NVs. So we have to check very patiently which one is actually the NV and coupled. What happens in our experience? So if you look at the spectra, this green curve, for example, it looked exactly at 640 nanometer. And if I zoom this green line and show to anybody, everybody trusts me that this is a cavity mode at 640 nanometer. But this is actually a background cavity emissions, and it is getting enhanced due to the cavity. So it is not actually NV center emission spectra, even though it shows at 640 nanometer. So we have to really do a PL spectrum, may not be trustful. You have to really do a lifetime measurement and see as it is indeed a cavity coupled NV center. And then even if you get an NV, it can happen that it may not be coupled to the cavity. Because during the fabrications, you are not sure that how the sample get agglomerated. And when you make another film, it can give a lot of local stress and other things. So structure can become very bad. So nevertheless, we catch an NV center, let's say, for example, this one, and we measure the emission spectra. This is the blue line here. And you can see that it is peaked at around 640 nanometers. And if you compare this inset picture, the red one is the NV in a off cavity sample, and the blue is on NV. So you can see that this much phonon side band is suppressed here, and this much phonon side band is suppressed here. And we try to get the maximum emissions at 640 nanometer, which is a zero phonon line. So PL spectra confirm that there is a cavity effect, and the actual measurement is a lifetime. So when with the NV, which is in 29 nanosecond in the glass substrates, or if an off cavity sample, it reduced to 25 nanoseconds. So when you do our actual sample, you can see that the lifetime or the decay rate become much faster. The lifetime becomes 6 nanoseconds. And this is actually the Purcell effect, where you trap a emitter in an electromagnetic environment and try to modulate its emission properties. Now the question is, do all your NVs behave like that? Answer is no. Okay, so we did a lot of measurements and we picked up many NV centers. Some may be very good coupled with the cavity, some may not be that much. So it can also happen, even though your samples are very nice, even PL spec also show, your all NVs may not couple with the cavity. So it is a bit more stressful experiments, and the sample growth is the main key factor here. If you have nice sample growth techniques, you are controlling these emission parameters is very interesting. And you can see that at any rate, the samples shows a better decay rate compared to the reference sample. And this is at 640 nanometer. We did it for 660, 700, and 600 nanometer. So to verify all this repeatability, and so we have the single layer. Then I come back to my TAM structure. So we grow this sample in collaboration with IIT Kharagpur. So they grow this sample for us, this TAM structure. You can have this dielectric layers, then there is a spacer layer, which is NV's doped, and you have a silver layer. And we got the sample. We have a micro reflectivity setup in our lab, which is even published in this journal, how you can build this setup, because you have to do local measurements. You cannot do any conventional spectrometer or anything, because the sample, the spot size should be below 5 micron or so. So we measure the reflectivity. This brown line is without any cavity. So you get the very good old DBR band gap. And when you have a metal layer, you see the TAM mode is appearing at close to 640 nanometer. And I show this spectrum very intentionally. You can see that this TAM mode is fluctuating wherever, it depends on where you measure it actually. Because again, it relates to how your NVs are coupled with the TAM structure. So it may not be all NVs coupled very equally. Even though in the literature, people show that everything is intact, probably the one measurements. So it's very important to have statistical measurements, as many as NV is possible, so that you get a complete idea how these NVs are coupled to the TAM mode or a cavity mode in general. And we mount the sample in our confocal, and we got some NVs, bright NVs coupled with the TAM. And the black line is the reference measurements about the reference sample. And when we have a TAM structure, you can see that it tried to peak around 660 nanometer. That's where the cavity is made of. So you can suppress the phonon sideband here and here, and only try to excite the mode very close to where your cavity mode is designed. And the most important measurement is the decay rate. The reference is slow, but the sample show very, very fast single photon emission. Sorry, not single photon, very fast emission of light. And once you have a single NV center, we can have a bright single photon emissions, because the NVs in a medium emit, let's say 30 nanosecond lifetime, we can come down to around 7 nanosecond lifetime using cavity coupled structures. So this is something which Fani detailed talked in the previous slide. Recently, we are successful in developing a particular detect magnetic resonance. And thanks to Fani for all his help, we were struggling to set it up. And we can, as it go back to the basic energy level diagram, can lift the population, it can come back by spin conserved or spin selective transitions. Then you apply a microwave, you lift the population between these two, since this become the dark state, and you see a dip in the fluorescence intensity. This is something we simulated by solving the Hamiltonian of the systems. But this is a few weeks back, we successfully measured it. This is with the magnetic field is 0. We get a nice ODMR dip at 2.87 gigahertz, but the contrast is very less, only 5%. And when you apply magnetic field, you could see the Zeeman kind of split. The dips, the peak is separated into 2, 1, because now the degeneracy of these levels is lifted off. So we developed this also. We struggle a little more here rather than Hanbury-Brown-Test experiments. But I was so happy to show you that we got it in our lab. And maybe this is my last slide. Often the question asked to me is there any other defects in NVs and diamond, or this is the only defects possible? As I said, one of the things which is we are also now started, and many are also interested, is other than nitrogen vacancies, silicon vacancies in the sample. Okay, so structurally it is slightly different, because this is a split vacancy. It does not come in a lattice point, but rather between two vacant positions. So we got this sample from of our friends, and we measured in our lab, and we could see that the zero phonon line is around 739 nanometer. And most of the phonon sideband is gone away. So this is a system which is quite interesting without much phonon contributions. And this is recently we started also the measurements on hexagonal boron nitride, where you have a 2D materials. We created defects by in electron beam irradiations, and we created very site specifically, not random. We have a control where we wanted to create, and we got a sample where we created this close to the edge, and we measured the PL spectra. You can see that it is a very nice zero phonon line compared to the diamond sample. So this will give around 50% debye factor, which is a very interesting system, probably replace diamond in future. So with that, I conclude. I hope I able to convince you some interesting aspects of NV centers, especially coupled with the photonic structures, and why we need this photonic interface to modulate the emission property so that its usability in application become much more richer. And some of the activities right now we are happening in the lab is we are trying to image a single emitter or a single photon source and try to make a own demand deterministic single photon sources. And we are getting a cryostat this week, most probably. And so we'll able to do, once we have, we're able to do low temperature measurements. So these are some of my highlights of the talk we talked. And before I stop, I thank my students, the current students who are working on different aspects of diamond or other emitters, and my previous students, and my funding agency, especially the QSET program, where we got some money to set up this experiment. The Sona Jayanti Fellowship, we could get these low temperature based experiments. And my collaborators, Anant and Anand make our cavity structures, Shiva make us TAM structures, and funding for the ODMR help. And there is a funded postdoc available in my group if any of you are interested, or if your students are looking for it. Thank you very much. We recently had a flood in IIT Ropar, where in the northern part of India completely rain, and this was a nice sunshine, and there was a rainbow. I captured it. This is our institute gate. It's a pretty new institute, 13-year-old. Please welcome to visit our institute anytime. Thank you for your time. Yeah.
So this, I mean, this plot at B is equals to 0, this looks like something like an airy pattern inverted for some reason. But I mean, when you are fitting it, you are just fitting it a bias line with it, but you are not fitting these oscillations.
No, it's just a random fit. Just wanted to show
Okay,
this.
this
I
is a
said
random
that
fit
we have not
only.
done anything very
Okay.
concrete on it.
But what are the reasons for these oscillations?
No, I do not know right now the reason. So it could be any sample impurity or anything. I do not know because we have not analyzed this data. I said we just wanted to show you. So happy with that. At least we could get this ODMR dip in our lab. Yeah.
No, I don't say signal to noise is bad. It's quite good. Actually.
So we are not analyzed or anything on ODMR. That's why I just show one slide to show you that yes, indeed, it is possible. Yeah. Yeah.
What is the expected line with
13 megahertz.
13 megahertz. So typically nanosecond, that will be the lifetime in that case.
Yeah.
Why do they not look like straight lines? I mean, is it?
It's a double exponential.
Why is it a double exponential?
Because there can be some graphite impurities in the surface which can give a very fast decay.
It seems like your whole thing is dominated by the second.
Yeah, second, because that is where from the NV center it is coming.
But then your, I mean, if you go back, you are plotting even some of your, not even the earlier one, actually the colloidal ones.
Yeah.
Not even starting from 1 when you start your fit. So
because there is some instrument response function thing. So we just start with the 1 nanosecond only. Yeah, you're right.
Okay.
Yeah, so you showed the Purcell enhancement. So looking at the lifetime, it looks like the Purcell enhancement is of the order of 5 or so.
5 or 6. Yeah.
So I was wondering, like, if you already use this photonic crystal cavities where you immediately have a very high Q and a very low modal volume. So what is exactly limiting you?
Okay. What you're saying is right, but those are all simulation results. Okay. So if you look at any photonic crystal cavity papers where people simulate, it shows Q factor very high and expected lifetime is the Purcell factor of hundreds. But actually, when you do the real experiments, the changes are only 5, 6 only. Because there, what happens in experiment, you have a lot of disorder in the sample. So that will kill you a cavity effect. Okay. So having this 6, 7 Purcell enhancement is still a good number comparing the easiness of fabrication of the samples and experiments.
Okay, but I think the state of the art, like Purcell enhancement with this photonic crystal cavities, especially, I mean, some papers I know of like have an enhancement of around 100 or so.
Yeah, I agree with you. But the amount of effort you have to put out to make that a photonic crystal cavity, like a 2D photonic cavities, and then you get an effect like that. Compared to that, our proposed system will be much more easier to do it.
So it's mostly the fabrication effort, not
the fabrication effort. And so one can even more, we did some simulations. We can even go to some 20 or 30% Purcell enhancement by doing some more modification in the structures. Okay.
And also in the cavity coupled NV center you showed, the spectrum looked quite broad to me. Like, is it because of the phononic side?
Yeah, because this cavity, as you said, it is not a very high Q cavity. So there is some 30, 40 nanometer in the weight. So that will get enhanced. Okay.
Yeah, thank you.
Is it possible to put these defects in some array? May not be in diamond, but in other kind of material platform. And also you're working with super hard. So is it possible to engineer defects at the specific locations?
So the super hard approaches that we make diamond samples and you test it and see whether we have a single NV center. So we did a Hanbury-Brown TIS experiments. We didn't get any dip like a single photon emissions. So those are all mostly ensemble of things. So once we are able to create preferentially, we are confident that we got a single NV center, then probably we can make it an array. Okay, but what we did, maybe it is just, we submit the revised one. I'll show you one thing we did. Okay. So here, what we did, we have a hexagonal boron nitride. We took the sample, and so they created using electron beam radiation the defects here. So one can also create electron beam radiation here, and you can create a defects here also. So you can get a site-specific defects. And there is a report in literature on HBN where people use a femtosecond lasers and scan it and created defects like a line defects. So you get a one emitter here, another here, another here. So it is possible.
I have one small question. You showed that G2 measurement.
Yeah.
Why is it only about 0.4 or so?
It is not my measurements, it is from literature.
Is
but
there something better? I mean,
yeah. I didn't show
close
you.
to 0?
Yeah, I didn't show you because we have not done much analysis. This is our measurements. We got it's 0.1. Okay, because it's not published or we have to do some more things. So this is 0.1, we got it. This is from single NV sender in diamond, not from nano diamonds. And this is from 2D material, we got 0.25 HBN.
Okay.
Yeah. We can get it very close to 0. Any questions? Please, please. I do not know that whether strain can change 640 nanometer, but I have seen some work in literature where strain is used in 2D material to create defect states.
Yeah, I was asking for.
No, I do not know whether strain can create a shift in the 640.